So let's start the last talk in this morning semester. So it is a wonderful conference in honor of 16th birthday. So I'm very happy to participate in this conference. So I'm honored to introduce Professor Jian Song talk. He will talk about geometric analysis on singular complex space. Yeah, please.
Thanks.
Okay.
Thanks, Xiaohua. First, I'd like to thank the organizers for the invitation at this very special occasion. It's my great pleasure and honor to have been collaborating with and working with Professor Tian since when I was a graduate student in 2003. And it has been exactly 20 years, a wonderful and fruitful collaboration. It's also, I'm extremely proud that we're still working together and producing fascinating results in our original program and goal. And in the Chinese, there's a Chinese old saying, beyond the skies, there's another sky, if you know Chinese. All right. Well, you can see the pun here. So we can also say that beyond the skies, there's also a commanding land of mathematics. So happy birthday, Tian, and more theorems on the way. All right, so I'll talk about some recent results. I'll talk about some recent results. With Bing Guo, Fang, and Jacob Stern. Bing and Jacob are my colleagues at Rutgers. So let me give some outline of the talk. I'll give some background, then we'll talk about some uniform geometric estimates for Kähler matrices with only entropy bounds. And also then we push these estimates to singular varieties so that we can handle the geometric analysis, both analytically and geometric, for singular Kähler spaces. And then we'll talk about some applications in relation to Ricci flow, canonical Kähler matrix, and also possibly with the He kernels for singular varieties. So let me say a few words about the background. Suppose M is an n-dimensional closed Riemannian manifold. We always assume there's no boundary. Okay. Then there's a classical Sobolev inequality on this closed manifold, so that the optimal exponent will be 2n over n minus 2. So it's bounded by this LP norm is controlled by the W12 norm of F for any F in W12. And then, of course, you can talk about the He kernel, talk about the Green's function, the estimates for the Green's function, the lower bound and the gradient bound. You can also talk about the kth eigenvalue of the associated Laplacian operator. And you can obtain the lower bound. For example, the kth eigenvalue can be controlled by a multiple of k to the power of 2 over n. All these exponents are related for a fixed metric. So of course you want to look at these uniform controls, like these constants, Sobolev constant and the constant of for the bounds of eigen values. So naturally, from the 70s and 80s, Yao and his collaborators, particularly Chen and Peter Li, they can control these constants uniformly. If the manifold, the family of the manifold satisfies a uniform Ricci curvature lower bound, and then let's say the diameter upper bound, and also the volume uniform volume lower bound away from 0. So once you can control these geometric quantities, in the Sobolev inequalities or the eigenvalue estimate or He kernel estimate, like trace estimate or Green's function, all these constants can be uniformly bounded. These constants only depend on, for example, these three geometric quantities, particularly the Ricci lower bound, in this case. If the volume is collapsing, you can still do some normalization. You can get quite a few effective estimates. Well, the problem is, is it possible one can replace the geometric dependence of these bounds, for example, subdefinite quantities, heat kernels, eigenfunctions, and Green's functions, by analytic and algebraic dependence, just as the first talk by Aaron today? Is it possible to replace these geometric quantity by certain energy control? And also, one naturally would ask, can such uniform estimates hold on complex varieties with singularities, especially these normal singularities? You want to push these uniform geometric estimates or geometric quantities to live on singular varieties. Okay. So we started this kind of research in this direction a while ago. So with Xingfu, Bing Guo, many years ago, we tried to use the idea from the pluripotential theory to control diameter bound. Well, if you look at, so this is what we prove. We show that given a Kähler manifold with a fixed Kähler metric theta, theta is going to be fixed. Then we look at all the Kähler form in the same Kähler class of theta, which is omega. As long as the following two conditions hold. The first one is the volume measure condition, which means the volume ratio is uniformly bounded by LP for some P greater than 1. And then the second condition is that Ricci curvature is bounded from below. Then you have uniform diameter upper bound for this space, for X associated with, equipped with this varying Kähler metric. Well, this condition is rather natural because it started from the Yau-Salisbury solution to the Calabi conjecture. Because given a prescribed volume form and a given Kähler class, you can always solve the Monge-Ampere equation with respect to this volume form up to some scaling. You get a smooth solution. Then the natural question is the dependence of your estimates. And turns out that this is exactly the estimate by the fundamental work of Kowalczyk. He dramatically improved the estimates by saying that the right-hand side is only required to be LP for some P greater than 1. Earlier, I think Chen and Yao, they showed that if the P is equal to 2, you can solve the Monge-Ampere equation. In fact, Yao has already tried to solve the singular Monge-Ampere equation in his original paper. Half of the paper is on the singular setup. Now, of course, initially you wouldn't realize why this integral condition for the volume ratio would be so important in geometry. Turns out that the fact that P greater than 1, this condition, exactly coincides with the algebraic notion of KLT singularities. So this is exactly what one needs when you have geometric applications. Right? So the second condition we still require is Ricci lower bound. So, and then we get the diameter upper bound. Now, naturally one would ask, can you remove the Ricci curvature assumption? Only the volume control, which can be viewed as certain energy control. So you don't need any other control. As long as the volume measure has certain LP control, then you should get diameter bound. This corresponds to certain boundedness property of the Kähler manifold. So our goal is to first, at that time, to remove this. Okay. And then this is our setup. Instead of look at LP normal, you can look at even weaker assumption. This is the volume measure, omega n to the fixed. You have a closed Kähler manifold with a fixed Kähler metric. And then you look at the varying Kähler metric omega to the power of n, and theta x to the power of n. This is the volume ratio. You look at the varying Kähler metric and look at the volume ratio with respect to a fixed volume measure. You can see this is a little bit, looks like a little bit in the setup of optimal transport in RCD space. And then you look at the total integral, the LP integral of this log log of the volume ratio with respect to the change of the varying volume flow. And P has to be strictly greater than N, the complex dimension of X. So we call this P Nash entropy. This can be defined for any Kähler metric, smooth Kähler metric on a given Kähler manifold. And we define the space of all Kähler metrics with respect to these parameters. X is the Kähler manifold. Theta X is a fixed Kähler metric. Right? N is the complex dimension. A is the intersection number of the given Kähler class omega and n minus 1 power of theta x. It essentially basically bound the Kähler class in the Kähler cone, but it could degenerate in terms of its volume. So the total volume could be arbitrary. And then we require a uniform entropy bound for the volume measure, right? Because the Ricci curvature essentially is more or less just related, associated to the volume measure instead of other quantities, right? So essentially, this is all we need. The intersection number, control of the Kähler class in the Kähler cone, and then which could allow degeneration, and then the energy bound. Then we have the following results, recent results. Essentially, it says there exists a constant d that only depends on these parameters. No curvature, there's no curvature assumption at all. The diameter will be uniformly controlled, bounded from above. Right? The volume could collapse. And then you have the Sobolev inequality for all of these Kähler metric. Again, no curvature assumption. But here the drawback is that the Q is only, we know some Q greater than 1. It's not to the optimal exponent n over n minus 1. Here n is the complex dimension. Now, if we use the original Kowalski's assumption where the volume measure ratio is LP for P greater than, for some P greater than 1, then this Q can be chosen arbitrarily close to the optimal exponent n over n minus 1. Of course, the constant might blow up. So this essentially in geometric application, the Sobolev inequality is almost optimal, almost optimal. The reason it's not quite optimal, well, in fact, it's not going to be optimal because we don't have any curvature assumption. So of course, if you assume some weak curvature assumption, we expect that Q would reach the optimal exponent. And you can see that since in our definition, we don't assume the Kähler class to be non-collapsed or uniformly bounded. You only need this linear intersection number to be controlled. So the volume, it's just that the total volume doesn't go to infinity, but it could degenerate. So you can allow the Kähler class to approach the boundary of the Kähler cone, meaning it could degenerate along certain subvarieties. The EMPO class, the EMPO locus is kind of sort of a Zariski open set in X. Or it can be totally collapsed. Right? The volume could go to 0, totally collapse. So in our theorem, in fact, it doesn't matter. Even if it collapses, even if it degenerates, we still, the Sobolev inequality is still uniformly held. And except that you have to put in this normalization constant I omega to make it into a scaling invariant. Right? So this is our main result for the smooth case, where we establish the uniform control for the quantities. So I would like to remark that our original theorem requires a small degeneracy assumption, meaning there exists a non-negative continuous function, gamma, such that the vanishing set of gamma has Hausdorff codimension strictly greater than 1. And that the volume ratio has to be greater than or equal to this gamma. This condition is purely technical because in terms of applications, it always holds because usually we choose the vanishing set of gamma to be an analytic subvarieties. But very recently, just within 2 weeks, we are able to remove this assumption. So all you need is just the energy control. So this assumption was almost simultaneously removed by Wu and Gage, Tao, and ourselves. So Wu's case is a bit weaker because he used our Sobolev inequality to only to derive the diameter estimate without this assumption. But then it turns out it's a quite straightforward technical improvement. So now we only need the energy control. The entropy is bounded. You get all the geometric estimates. Not quite perfect though. Using the Sobolev inequality and the diameter control, then you can basically get all the heat kernel estimates. So if you, for example, you look at the trace formula for the heat kernel, you get almost the same identical estimate as in the lecture notes of Shane and Yao, T to the power of Q over Q minus 1, Q minus 1 over Q. Of course, it's not optimal because Q is not equal to N over N minus 1, but it can be arbitrary close. Okay. You can see that it cannot be arbitrarily close because the volume measure could be vanishing. For example, on S2, on CP1, the volume measure can become degenerate so that near the equator, everything goes to 0. So you would imagine that the isoperimetric constant will fail, and therefore you miss a little bit. So therefore, you need a little bit sort of non-collapsing condition or sort of Ricci curvature, weak Ricci current condition to exclude these degenerate case, to guarantee that the exponent can reach the optimal one. And also you can get the eigenvalue estimate, the lower bound for the kth eigenvalue estimate, exactly the same as the classical one, except that Q is slightly off. And you have to put in these normalization constants. Right? So, and also you can get the Green's, the bounds for the Green's functions. So Sobolev, Green's functions, diameter, eigenvalue estimate, heat kernel, you can basically get whatever you would like to have. Of course, the next step is to push these estimates to singular varieties. Right? In the setup of complex geometry, the singularities are fairly easier to study compared to the real ones, which is too wild. Thanks to a lot of work done in the classical several complex variables and also birational geometry. Right? So here we assume that X is an n-dimensional compact Kähler space with normal singularities. Again, there's no boundary. Well, of course, you can view the singularity as the boundary. So the normal singularity, basically, they have complex codimension 2 singularity. So they're outside codimension, real outside codimension 4, it is smooth. Right? And of course, we can have a resolution of singularities. Right? So Y is, you just pick one non-singular model of X. And of course, since it's Y, you can pick a Kähler metric on Y. And we let X circle to be the regular part, the smooth part of X. Right? So for any singularities, well, thanks to the resolution of singularity, we can just go to its non-singular model. And we define a similar space as we did before for V. So here we assume that this AK space is a set of Kähler currents on X. Well, as a positive, it's not Kähler. You don't even have to. They don't even have to be Kähler. They just have to be positive. A positive one closed currents on X, such that the intersection number with a fix, you put it back, and it corresponds to a Kähler class, but not degenerate Kähler class of semi-positive class. The intersection number with respect to a fixed Kähler class on its non-singular model is uniformly controlled. This guarantees that the class is not going to the infinity. The volume doesn't go to the infinity. And then you can define the same P Nash entropy with respect to this theta y, the Kähler, smooth Kähler metric on the upstairs on the singular, non-singular model. And you do the same kind of a P Nash entropy for the volume measure, except that you just put everything up on the non-singular model. You just look at the LP norm of log of the volume ratio. And it's uniformly bounded by K, P greater than N. So certainly if the LP norm of the volume ratio is bounded for some p greater than 1, the Nash entropy is naturally bounded. Okay? And we require that the volume ratio is smooth on the regular part. Well, in fact, we require log of it to be smooth. The reason log of it to be smooth is to prevent that it's simultaneously 0 on some smooth part. You want omega to be a Kähler metric on the open set, open manifold X circle. You don't want it to drop to 0. So at least it's a Kähler metric on the non-singular part of the singular variety. So essentially, the assumption is the same. These are the two key assumptions. The cohomology class control in terms of intersection number, and then the entropy control. Well, so we know that since the singularity, it's a normal variety, the singular set of X is an analytic subvariety of X of complex codimension 2 at least. And then for any omega in the previous, this so-called AK space, omega is a smooth Kähler metric on the regular part, on smooth part of X. And omega has bounded the local Kähler potentials. This is because of, similar to, by the work of Kowoje, and also the improvement to the degenerates by Studiu, Gadge, and Zeraki, you actually can show that the potential is actually locally bounded and actually continuous. So we know that on the regular part, the smooth part of the singular variety, the Kähler metric is smooth. And then why don't we just take the usual metric completion? So the metric completion will give you a complete metric space. So we call it X bar D. And D is the distance or the metric induced by the smooth Kähler metric on the regular part. And don't forget, we have the original Kähler metric as a Kähler form. You take the top wedge product, it gives you the volume form or measure. So you look at this metric completion coupled with this volume measure, you get a metric measure space. So this kind of a Kähler current or positive current immediately gives you a metric measure space. Of course, when you take the metric completion, this is a wild metric space. You have no idea how is it related to the original singular variety. Of course, it has an open regular part, which coincides with the original complex variety or algebraic variety. But of course, we wish there is certain intrinsic relation between the analytic side and the algebraic or complex side. But this is what we can prove, right? So for given an n-dimensional compact normal Kähler space, you pick any Kähler match, positive current, satisfying those two conditions. The cohomological condition where the top intersection number, the linear intersection number is controlled, and the Nash entropy is controlled. Then the metric space, the metric completion of the regular part using the smooth Kähler metric, the diameter is uniformly bounded. And also, you have Sobolev inequality, just like what we did it before. And there's no ambiguity how you choose the Sobolev space. You can choose it to be the metric completion, the compact metric measure space, or you can just replace it by the usual algebraic sets. You just pick the original algebraic variety. This is because the singular set has codimension 4, and we are able to ignore these discrepancy. Essentially, the singular set in this case, with respect to this Kähler current, the capacity is equal to 0. So you can just move between the algebraic side and the analytic side. There's no barrier between them. Okay, thanks to our assumption that the energy is controlled. Well, once you have the Sobolev inequality, again, you can just establish the spectral theory for singular varieties. You have a metric on it, you can look at the Laplacian, and you can look at all the eigenfunctions. So all these eigenfunctions, they're bounded, they're smoothing where everything is smooth. So you have all the nice structure for these spaces. So let me say a few words about applications. Okay? Well, so as our assumption, you look at the compact normal Kähler spaces, and then you can get similarly uniform bounds for the Sobolev constants, control of the Green's function, including its gradient, the L1 norm of the gradient, the heat kernel trace estimates, eigenvalue estimates. And also you can just apply Moses iteration on both linear and nonlinear PDEs on singular varieties. Before, once you have singularity, usually what people do is just using the pre-potential theory or use certain maximum principle constructing barrier. But now you can just treat the singularities just like smooth varieties. And I see a few words about the canonical Kähler matrix on X, especially the Kähler-Einstein matrix on singular varieties. And also, this estimate provide bounds for finite time and long time solution of the Kähler-Ricci flow. And also, we have spectral theorem for singular Kähler varieties. And this is particularly useful because it was, we will see the connections to the RCD space as a generalization of Chico coding theory. So let me say a few words about singular Kähler-Einstein spaces. Let's just look at the case when you have normal varieties with ample canonical class or Calabi-Bial case, but they're singular. And assume that they have KLT singularities because you want to have certain boundedness. And then you can look at on the regular part, you have a unique Kähler-Einstein current. This is known a while ago originally by the work of Asidil Gadge and Zerahi almost 20 years ago, based on the work of Kowalczyk, the LP estimate, the L infinity estimate based on the LP bound on the right-hand side. So we can show that if you look at the metric completion, this Kähler-Einstein metric space is a compact metric space. Furthermore, you put in the volume measure on it. This is a compact metric measure space where you have Sobolev inequalities, diameter control, heat kernel estimate, and eigenvalue estimates. So on the singular Einstein space, you have a lot of things to do to derive. Of course, the exponent is again a little bit off. It can be arbitrarily close to the optimal one, n over n minus 1, but at the moment we are not able to do that. Of course, the conjecture, well, this is kind of a sort of a folklore conjecture. We want to show this is a metric measure space of the Kähler-Einstein space. It is homeomorphic to the original algebraic variety. So you have algebraic variety with a regular part. Then you go to the analytical side, solve the singular Monge-Ampere equation, you get a Kähler-Einstein current. And then using the Kähler-Einstein current, you get a metric completion, you get a compact metric space, which is Einstein almost everywhere. That it goes to the geometric side. So then the question is that can you complete the diagram that the algebraic variety is the same as the analytically controlled constructed metric space geometrically, they're the same. Right? This is essentially saying, of course, you assume these have KLT singularity. So this is where the algebraic structures meet the geometric structures going through the analytical PDE arguments. And well, we're working on this. Well, I think this is within reach. It seems that it's not. It's probably within reach. And the conjecture holds in complex dimension 3. Okay. In fact, you can even show that all the tangent cones they're algebraic. They can just so dimension 3 essentially it should be done very soon. And also we can look at the application to the Kähler-Ricci flow. So you start with any Kähler manifold with any initial Kähler metric, you can run the usual Ricci flow. We know that the Ricci flow preserves the Kähler condition. So it's a Kähler Ricci flow. And the advantage of the Kähler-Ricci flow is that you can predict the first singular time easily because it's just it can be calculated just in terms of cohomology condition. As long as the evolving Kähler class stops being Kähler, then that would be your first singular time where the curvature has to blow up. Right? So the flow exists from 0 to this capital T. We know that exactly this is sharp. And this is in fact derived by Professor Tian and Zhou Zhang. And for the finite time solutions, in fact, we can show that if the volume doesn't go to 0, which again is can be calculated in terms of cohomology intersection numbers. So the metric converges outside the analytic subradial axis smoothly. And the diameter along the finite time Kiloricci flow, solution of Kiloricci flow, the diameter is uniformly bounded. And in the limit, you take the metric completion of this regular part, it would be smooth, it would be a compact metric space. You have Sobolev inequality that holds both on the solution and the limit metric space. And also, Tian and I, in our so-called minimum model program, analytic minimum program with Ricci flow, we conjecture that this limiting metric space should be homomorphic to the algebraic contraction of X, related to the flips and divisorial contraction. So this is true in complex dimension too. Ben Weinkoff and I can do that. Our method cannot be applied to finite time collapsing case or extinction because, for example, the Perelman's diameter bound for the final Ricci flow cannot be derived from our approach at all because we have the entropy bound. In the Perelman's work, there's only L1 bound. In our approach, essentially, we need LP bound for some P greater than 1. So this is the subtle difference between L1 and LP, where the gauge transformation kicks in. For the long-time solution, you look at the Kiloricci flow has long-time solution if and only if the canonical class is NAF, meaning it's a minimal model. So we can show that originally with Wang Jian in Beijing, and we show that as long as the canonical class is semi-ample, the normalized solution has uniformly bounded diameter. This is optimal. So our approach is to apply what we did earlier with Tian and Zhenglei Zhang and Tian and Zhenglei Zhang with myself, coupled with the recent work of Bemler to derive the diameter bound for a long time. But recently with Bingguo, Fang, and Jacob Sturm, we're able to get the diameter control as long as it's NAF. So essentially, the diameter estimate is not that geometric. You don't really need that much of a curvature condition to get control. And of course, the scalar curvature is uniform bounded. Well, we assume that's semi-ample. This is the work with Tian a long time ago. So combine these two together, you have diameter bound, you have scalar curvature bound. That corresponds to the long time analog of Perelman's famous diameter and scalar curvature bound for finite extinction solution. So my time is up, and thank you.
So thank you, Jian Song. Wonderful talk. So any question or comment? So your solution just for Sobolev space, right? Not for current sense.
The current sense, no, they're actually bounded. These but if you can look at eigenfunctions, they're W1, 2. You can just they can view it as current, so you can view it as usual on the regular part. There's no actually ambiguity between among these.
Okay, question?
For dimension 3, why dimension 3 is special? Again, that dimension 2 because all before the points and so on. Dimension 3,
dimension, of course, yeah. Dimension 3, of course, dimension 2 is easy because you only have orbifold singularity. For dimension 3, the singularities are not even locally smoothable. So we use sort of, we can identify, we can essentially show that you have to use certain RCD space. We were able to show that as long as the eigenfunctions are Lipschitz, well, then you can show that this is RCD space. Using RCD space, you can jet up and sort of do the your partial C0 kind of estimate. And because dimension 3, you have sort of a very complete understanding of the singularities by Reed's work and other people's work. So dimension 3, it can, but I think in high dimension it can be done. It's within reach. It's not too far away. I think it should be done in the near future. I believe.
So dimension 3 has 10 and Lee has regularity for
No, you can have a partial, not quite, because essentially you know that codimension 2, they're orbifold singularities, but you have codimension 3 singularities. Codimension 3 are kind of the most difficult singularity is the terminal singularities. So even in dimension 3, they are not locally smoothable. So if it's all smoothable, of course, you can just using Cheeger coding theory to apply it. But the problem is that even in dimension 3, globally and locally, they are not smoothable. So you have to get some new ideas, like using what we did to build up the spectral theorem for singularities, and you just push analytically to do it.
Okay, so for general case, finite time block, you cannot estimate.
Flow is much harder because it corresponds to the L1. But recently with Tian and also Wang Jian, we are able to give a new proof of Perelman's scalar curvature and diameter estimate for finite time extinction, and that which can be generalized to any finite time singularity. But of course, not perfect. But at least we get compactness to certain point.
Okay. Oh, yeah. Very good.
You probably mentioned, does this program give an approach for partial C0 estimate in final case?
Not really. The partial C0 is essential because once we have these estimates, as long as you can identify it as kind of sort of RCD space, then you can sort of do the tangent cones. These are good tangent cones. Then you can play around and get the partial C0. Then come. Then that part is, I would say, relatively now standard. The key is that to build up the analytic tools, so you can sort of identify, for example, to enhance. The key is to understand the eigenfunctions, the regularity of the eigenfunctions. The geometric side is, at the moment, is getting more standard, I think. And I should say also that Gabor Zakhlidi also, he has done some work which is beautiful. He looked at the collapsing limit using our estimate, especially the heat kernel estimate. You can look at the collapsing, but Tian and I consider it's twisted K-Einstein space. You can also get certain algebraic and geometric correspondence using also through the RCD space structure.
So it's okay. So if no questions, so thank you.
Thank you.
Yeah, again.
Happy birthday, Tian. Happy birthday.
Thank you. Thanks for coming. We'll see you in Beijing.